Okay, so now let's take a look at the MOSFET qualitative theory with the long channel current versus voltage. We're going to study the square law theory, definitely. So in this lecture, we will delve deeper into the theoretical aspects of MOSFETs, focusing on qualitative theory and long channel current voltage characteristic, often called the square law theory. So this will move us from understanding what MOSFETs are to how they actually behave in circuits. So think of today's lecture, as learning the anatomy of a car, identifying the engine, transmission, wheels, and steering system. So in this lecture will be like understanding how these components work together when you press the accelerator or turn the wheel. So we will explore how voltage applied to the gate affects current flows through the channel, and how the relationship between drain current and drain source voltage defines different operating regions, such as saturation region, linear region, blah, blah, blah. So the qualitative theory will give you an intuitive understanding of MOSFET behavior, while the mathematical square law model will provide the quantitative predictions. Just as understanding the physics of flight helps aircraft designers create better planes, understanding MOSFET theory helps circuit designers create better electronics. So come prepared with your questions from today's material as we are going to build directly upon these fundamental concepts. Okay? So now let's take a look at the qualitative theory of the N-channel MOSFET, NMOS. So let's examine the qualitative behavior of the N-channel MOSFET first. When the gate to source voltage is below the threshold voltage VT, the transistor is definitely in the off state. Imagine a garden hose pinched so tightly that water cannot flow through. Electrons face a potential barrier that prevents current flow between source and channel region. Once gate voltage exceeds the threshold voltage, the source to channel potential barrier can be lowered enough, creating an inversion layer or channel, as indicated here, which allows electrons to flow from source to drain. So this is like relaxing your grip on that garden hose. Water can now flow. The intensity of the flow depends on how much you loosen your grip, okay? How much VGS exceeds VT. All right. And with a very small drain to source voltage, here, with a very small amount of drain to source voltage, VDS is approximately zero, but say that 50 millivolt, the channel has uniform thickness from here to there. The thickness of the channel is quite uniform, like a straight pipe. As we apply a positive VDS, electrons flow from source to drain by drift. The channel potential varies continuously from Vs, here Vs to at the source end to Vd at the drain end. So imagine a pipe that gradually narrows from one end to the other end, affecting the water flow throughout. So this inversion layer can be modeled as a resistor when the current is directly proportional to the inversion charge density or Q inversion, and channel width and the effective mobility of carriers, mu effective, and inversely proportional to the channel length L. Okay. So here, the drain to source current is proportional to the channel width and how fast the electrons can move between source and drain, and how much carriers are conglomerated in a inversion layer, denoted as a Q sub inversion. So these three terms will determine how much drain to source current can flow. And here, as we have learned in the device physics, the thermal velocity is proportional to the electric field, and the coefficient can be can be written with effective mobility, right? And here, the electric field between drain and source can be rewritten with voltage divided by the distance, right? So here, the distance between source and drain is denoted as channel length L, and the voltage difference from drain to source is VDS, okay? So, the inversion layer can be simply modeled as a register, okay? When the VDS is positive and gate to source uh, voltage is higher than threshold voltage. So this relationship is represented by the equation at the bottom of the slide again here, showing how all these factors combine to determine the drain current. Just as a water flow depends on the pipe diameter, length, and pressure, so electronic current depends on the channel dimensions, channel width, channel length, and the charge density in the immersion layer, and applied voltage between drain and source. All right. So now let's take a look at the channel pinch off and saturation. So as we increase the drain voltage of our MOSFET, an interesting event occurs. When VD reaches Vg minus Vt, the inversion layer charge density at the drain end here. Think about here. At the drain end, the V, oops. At the end of the, why is that? Here, VGS is equal to Vt at this point. VGS is equivalent to the threshold voltage. A very tiny point can be formed as an inversion chart or inversion layer. If VGS is slightly higher than threshold voltage at this point, the inversion layer can be thickened out. Okay. However, if your drain to source voltage on the bottom side of at this point, VDS is equal to the voltage difference between VG and VT, then there is no inversion layer. A very small pinhole-like point can be formed at the drain end. Okay, so when VD is equivalent to the VG minus VT, the inversion layer charge density at the drain end becomes zero. We are saying that the channel pinches off. Okay, so think of this like a garden hose that's being pinched at one end. Water still flows, but it encounters a constriction. So this pinch off condition marks the boundary between the linear region and the saturation region of MOSFET operation. Once VD drain voltage exceeds Vg minus Vt, as described here, the pinch off point begins to move away from the drain toward the source, creating a depletion region of the length delta L here. So remarkably, the voltage across the remaining inversion layer stays constant at VD set of Vg minus Vt, regardless of how much we increase VD beyond this point. So this causes the current to saturate, hence the name saturation regions. So imagine water flowing from a reservoir through a pipe that empties into open air. Once the pipe is flowing full bore, making the exit higher or lower doesn't increase the flow rate. It's limited by the pipe's capacity, not the exit conditions. Similarly, once a MOSFET reaches saturation, the current is controlled by the gate voltage rather than further increases in drain voltage. This is the key part of the MOSFET operation, I think. For long channel devices, the drain current in saturation is given by the ID set, which is equal to IDS when the VDS is equal to VD set, which is VG minus VT. However, if delta L becomes significant compared against the channel length, we observe a slight increase in current, as shown in this plot. here, IDS versus VDS, the output characteristic of MOSFET. So if delta L is approximately equal to the channel length, in other words, the physical channel length is quite aggressively scaled down. The pinch of the region delta L is quite similar to the L. We may not see the saturation current. We must see a ever increasing, monotonically increasing drain to source current as increasing VDS. Um, so let me see. So again, if delta L becomes significant compared against to the channel length L, we may observe a slight increase in current with increasing VDS beyond the VD set. So this is called as channel length modulation. So channel length modulation effect becomes more pronounced in modern short channel devices like how water pressure effects are more noticeable in short pipes rather than long pipes. Okay. So now let's move on to the ideal MOSFET current voltage characteristics. Now you're seeing the output characteristic of the ideal MOSFET or long channel MOSFET. The current voltage IV characteristics of an ideal enhancement mode MOS transistor reveal the two distinct regimes of operation we have just discussed. Linear region occurs when VDS is small, and the relationship between current and voltage resembles that of a resistor. So as you can see here, as voltage increases, current increases, like a resistor. And mm, so, all right. And what about the saturation region? So as VDS increases and approaches VG minus VT, we reach the saturation region, okay, where the current levels off, becoming almost independent of the drain to source voltage. So this creates a horizontal plateau you see on the graph, right, for each gate voltage. The higher the gate voltage, the higher the saturation current level is, which is like how opening a valve wider allows more water to flow through a pipe system. So when VG is below threshold voltage, the device remains off regardless of VDS. So this is shown by the flat line here at the bottom of the graph. Once VG exceeds VT, the device turns on. Otherwise, the device turns off. And its behavior follows the pattern. Once the device turns on, all the behaviors of current versus voltage follows the pattern that I have just described. All right. So these current versus voltage curves are fundamental to understanding how MOSFETs function in circuits. When designing amplifiers, we typically operate in the saturation region to achieve good gain. For switches in digital circuit, we toggle between the off region and the linear region to achieve low resistance when on. So just as understanding the torque curves of an engine helps automotive engineers design better transmissions, understanding these IV characteristics helps electronic engineers, device engineers design better circuits. Okay. So now let's take a look at the impact of the inversion layer bias. So when a MOS device is biased into inversion, something important happens actually. A PN junction forms between surface here, PN junction forms between the surface inversion layer and the bulk semiconductor beneath it. Now, I'm talking about here. So inversion layer is N-type and the body is P-type. So again, when a MOS device is biased into inversion, something important happens. What is it? PN junction forms between surface inversion layer and the bulk semiconductor region. So this PN junction creates a fascinating situation where we can apply a bias to this junction, this PN junction, if the inversion layer contacts where heavily doped region of the same time N plus source. So imagine the inversion layer as a thin sheet of water flowing over soil. Normally, the water and soil interact in a certain way, but if we could somehow change the properties of the soil from below, we would affect how the water flows above. That's conceptually similar to what happens when we apply a bias between the channel and body. So in this diagram, we see an N-type inversion layer, the channel, formed at the surface of the P-type silicon. This inversion layer is contacted by an N plus region, allowing us to apply a bias voltage, say V sub C, to the channel. If we do this, a reverse bias, VB minus VC, develops between the channel and body. So this reverse bias affects the depletion region width beneath the channel, which in turn affects the channel conductivity or resistivity. So this event is critical for understanding body effect, how substrate voltage affects threshold voltage, and latch-up, a potentially destructive phenomenon in CMOS circuits actually. So it is like how the foundation of a building affects its upper floors. Changes below influence behavior above, even though they might seem disconnected at first glance. Okay. All right. Now let's move on to the next slide, which includes more complicated ones, equations. So take a look at the effect of V sub CB on surface potential, depletion width, and threshold voltage. So the application of a reverse body bias on MOSFET has several important effects on MOSFET operation actually. When we apply a reverse bias between the channel and body, say V sub CB, we create a non-equilibrium condition with two separate Fermi levels. One Fermi level for the N region, channel region, and the other one for the P-type region or body region. So think of this like two countries with different currency exchange rates. The separation between these Fermi levels equals Q times V sub CB, causing an increase in surface potential pi s by V sub CB. So visually, imagine pulling two elastic sheets apart. The separation increases the tension in both. So this increased surface potential widens out the depletion region with W and increases depletion charge definitely, Q depth. As a result, for a given gate body voltage, VGB, the inversion charge Q inversion decreases with the increase in VCB, okay? Yeah, here. So this relationship is crucial and critical for circuit designers to understand, especially in designs where the body and source are not connected to the same potential. You may see this situation in cascaded digital circuit logic block. So it is very similar to how how to say that meteorologists must account for both temperature and pressure when predicting weather. The interaction of multiple variables determines the final behavior. All right. Now let's move on to the MOSFET current voltage characteristic. Herein, the application of reverse body by okay. In a practical MOSFET, current flows from drain to source when the gate drain voltage exceeds the source voltage. Yeah, as I described here at the very first line, this current flows through the channel by drift. Electrons are pulled by the electric field from source to drain, like water flowing downhill. The voltage within the channel, we see of Y, varies continuously between the source and drain potentials. So picture a sloped water slide. The height changes smoothly from top to bottom. So this varying potential affects the local electric field and charge density throughout the channel. The mathematical expression on the slide describes the emergent charge density here. Emergent charge density as a function of y. At any point y along the channel. So it is noteworthy how this charge density depends on several factors. Gate voltage, definitely, and flat band voltage, the work function difference between metal and semiconductor, and the channel to body bias V sub CB as a function of Y, and, and the surface potential pi S, and the depletion charge Q sub dev as a function of Y. So understanding these whole relationships allows us to model how the drain current responds to the changes in terminal voltages. It's like how traffic engineers model vehicle flow based on road width, speed limits, and entry-exit ramps. The complex interactions between these variables determine the overall behavior of the transistor, allowing us to predict its performance in various circuit configurations. These models become increasingly important as we design more sophisticated, complicated integrated circuits with millions or billions of transistors. Okay. So now let's move on to the first order approximation. So to make our life easier, to simplify our analysis of MOSFET behavior, we can make a first order approximation by neglecting the variation of the depletion charge Q depth with position along the channel or with Y. Here, as long as we neglect the variation of Q depth with Y, uh, this gives us a more tractable expression for the emergent charge density as described here. Yeah, here. So where VT is threshold voltage at the source end of the channel, and this approximation is like assuming a garden hose has constant diameter, even though in reality it might vary slightly along its length. The threshold voltage itself depends on several factors here, as I have just told, including flat band voltage, source to body voltage, Fermi potential, the bulk potential here, pi f, and a term related to the depletion charge here. So these relationships allow us to predict how changes in bias conditions affect transistor behavior. So this first order model strikes a balance between accuracy and simplicity. Again, this first order model, not second order, third order model, the first order model strikes a balance between accuracy and simplicity. While it does not capture all the subtle physics of real devices, it can provide intuitive insight and reasonably accurate predictions for many, many applications. So it is very similar to how the ideal gas law does not describe all aspects of gas behavior, but it gives useful approximations under normal conditions. As we will see in subsequent lectures, this model forms the foundation for understanding more complicated behaviors and developing more sophisticated models. Okay. All right. Now let's move on to the MOSFET current. So using our first order approximation, we can derive expressions for the MOSFET drain current in different operating regions. So let's consider an incremental length dy, yeah, in the channel. The voltage drop across this region is dVc, creating a local electric field that drives current flow. So in the linear region, the current is given by IDS. IDS is equal to L over W. Here, let's see. in the linear region, yeah, IDS is equal to W over L, blah, 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 blah. So this quadratic relationship between current and drain source voltage explains why this is often called the square law models. Even in the saturation region, you can see clearly, explicitly see the square. It is very similar to how water flows in a tapering pipe, depends non-linearly on the pressure difference. The geometric effects create a second order relationship, definitely. So when we integrate along the entire channel region, accounting for how the channel voltage varies from source to drain, we arrive at this expression that describes how the drain current depends on the terminal voltages. The current increases with the gate voltage and initially increases with drain source voltage, but the rate of the increase diminishes as VDS grows because of the negative quadratic term. So this model provides mathematical foundation for understanding, transistor behavior in circuits, just as fluid dynamics equations help engineers design efficient plumbing system. These equations help circuit designers create efficient electronic systems, predicting how changes in one part of the circuit will affect current flow throughout the entire system. Okay. I guess you can simply derive this square root from those two, three lines, right? So this is basically the Ohm's law, and you can plug in double time, blah, blah, blah. You know the resistor can be described as a resistivity times a physical dimension, area, cross-sectional area, and the length, okay? So you may develop the whole equation. So by integrating both sides, you may end up with a total drain to source current, and that can be described with this uh, equation. So depending on the drain, PD is high enough or small enough, you may separate two different regions. Okay. All right. So today's lecture is the last slide in today's lecture, saturation current ID set. So when the drain source voltage reaches or exceeds VD set or VG minus VT, the MOSFET enters the saturation region. So in this saturation region, the current remains relatively constant despite further increases in VDS. The saturation current is given by IE set is equal to W over 2 times L times C equivalent oxide capacitance effective MOS VG minus VT squared. So this equation reveals several important insights. First, number one, the current depends on the square of the gate overdrive voltage, Vg minus Vt, overdrive voltage. And doubling this overdrive quadruples the current, right? Times two times higher V of V, overdrive voltage, results in a 4 times higher ID set, right? Because of this square. And what analogy? This is like how the pressure at the bottom of a water column increases with the square of the height. The current also depends linearly on the physical dimension, channel width divided by channel length, W over L ratio, width to length ratio of the transistor. So this gives designers a direct way to control current capability. Wider transistors conduct more current, like wider pipes carry more water. The oxide capacitance CXE and the carrier mobility mu effective are material and process parameters that also affect definitely the transistor's current. So the graph show on the left-hand side show how the drain current varies with drain to source voltage for different gate voltage values. Each curve initially rises linearly, then gradually levels off as it enters the saturation. Higher gate voltage here, higher gate voltage produce higher saturation currents. as it is expected from our previous equation that we have developed. This family of curves is a fingerprint of the device's performance, providing crucial information for circuit designers. Understanding these current versus voltage characteristics is like knowing the torque and power curves of different engines, essential knowledge for designing systems that perform optimally under various conditions. Okay. All right. So that's all for the lecture 26 slide. And in the next lecture, I'm going to talk about the MOSFET with effective mobility, bulk charge theory, and more. And in the end, the small signal model. All right. Thank you very much for your attention. See you next time.